Yeah, you have a quiz on Friday. You shouldn't need anything except for calculator, okay? You shouldn't need anything except calculator just to make it simple for you. It's stuff that we've been doing and been covering and been working on. So one of the things, though, I looked at you guys' homework, and apparently we have a problem. Now, by the time we're in this semester, I wouldn't have expected this problem. But it looks like I need to review significant figures. Okay, so let's review significant figures. If I write a number like this, how many significant figures is that? 5. If I write a number like this, how many significant number figures is that? 3. This is a placeholder. Remember that in order to figure out significant figures, the easiest way to do it is plug it into scientific notation, and this would be 10 to the minus 2, and that will tell me it's 3 significant figures. Okay? Now if I write a number like this, how many significant figures is that?
2.
Nominally 2. Unless I do something to tell you. Now if I do this, how many significant figures is it?
4.
It's 4. Okay? So, just as a reminder, apparently those were the largest missed homework assignments in the first couple homework assignments. And I went, huh? What? No, not you guys. That should have been a breeze.
That was probably me.
No, there were more than one of you. More than one of you. Because it was like 80%. Most everything was passed by 95% or more, and it's first try, right? 95% or more in first try. No, a couple of significant figure ones were at 70-something% first try. So somewhere along the line, people either were punching in wrong numbers or doing something, but significant figures. Now remember the importance of significant figures. Why do we care?
It's our accuracy.
It's the accuracy or the precision with which the number is known. The error will be in that last digit, okay? The error will be in that last digit. Now, most of the time in engineering, we are usually only dealing with 3 significant figures, but that's one of the things that we have to kind of be looking at. All right, so everybody's good with significant figures? If I give you a number that looks like this, and I want to round it to 3 significant figures, what am I rounding it to? 3.45. If I'm rounding this, what am I rounding that number to?
3.47.
Nope.
No, that's the...
I'm doing 3.46. The rule is saying that your number is even.
Oh,
That's right.
No.
Forgot about that.
Yeah, the rule is saying that when you round, you want that digit to be even. So in this case, I round down. If it's 3.455, then I round it to 3.46.
I thought if it was a 5, like that was the only odd number that was acceptable.
No,
It's the rule for.
it's the rule for this book. We round down. The idea is if I'm going down to here, now if I have a number that looks like this, 3.5658, and I round, then I would round up. But if I have just a 5, I round down because I want to leave that digit even. So I'm rounding up half the time, I'm rounding down half the time, so I'm not compounding an error. Now, if I have more digits past there, then I am rounding up because that swings it to the up.
It's like the hardest part of the whole class for me.
All right, so we got that. Okay, so where we're at right now is, so the quiz is basically over the stuff that we've covered so far. And where we were on Friday, I guess it was Friday, is it Friday? It's been a week. Is we were starting to look at vectors in 3 dimensions. We're starting to look at those vectors in 3 dimensions. So this is one way to do it, and this is looking in the polar coordinate system where I'm defining an alpha, a beta, and a gamma. Okay, so I'll have an AX, an AY, and an AZ. So that's one way of doing it. And this is giving me an alpha, beta, gamma route, or this is another way to do it. Okay, so I've got a theta and a phi, whereas this vector down here, this becomes an A prime vector, and my A prime vector is the projection of vector A into the XY coordinate system. Okay, it's the projection of vector A into the XY coordinate system. And all of this is leading up to being able to deal with a unit vector, is what we're actually wanting to be able to deal with. So if I'm writing a vector in Cartesian coordinate system, right? So my A vector is going to be an AX in the I direction plus an AY in the J direction plus an AZ in the K direction. The I, J, and K are unit vectors along the X, Y, and Z axes. So we can do that. We know the magnitude of this puppy is going to be the square root of AX squared plus AY squared plus AZ squared. But then it comes fun when we're dealing with those angles. So if I'm using this situation, okay, if I'm using that situation where I have an alpha, beta, and a gamma, I'm using that situation, alpha, beta, gamma, then the cosine of alpha is going to be AX over A. And these are magnitudes, okay? So that's really the magnitude of A. Cosine of beta is going to be AY over the magnitude of A. And the cosine of gamma is going to be AZ over the magnitude of A. Okay, so let's take it a step further here. And I want a unit vector, and we're going to write a unit vector as U of A. I'm going to want a unit vector A. So this will be a unit vector in the direction of A. Okay? So if I want a unit vector in direction of A, what I end up doing is I do AXI plus AYJ plus AZK, all divided by the magnitude of A. So if I do it in terms of cosine, the cosine ones, this is going to be the cosine of alpha, oops, cosine of alpha in the I direction plus the cosine of beta in the J direction plus the cosine of gamma in the K direction. So that's a unit vector A in the direction of A that has a magnitude of 1. Yeah.
Aren't these supposed to be squared? The cosines?
Nope. Nope. And if you want to follow along in the book, it's equation 2.5. Okay, so if I'm using this to get my unit vector along this direction, I need my cosine alpha, my cosine beta, and my cosine gamma.
So you just substitute in the original.
In the original, that is AX over the magnitude of A.
Yeah, and then cosine is equal to AX over A.
Exactly.
Okay, I gotcha.
Okay. And what's going to happen a lot of times when we're working these problems, so step 1, right, read the problem, right? That's, you know, that's well, not always. Step 1, read the problem. Step 2, draw the picture. Okay, step 2 is draw your picture. Step 3 is label things. Now, in statics, if you don't know what to do next, find the unit vector. Because that unit vector, we're going to do a lot of problems as we go forward, and we're going to need that unit vector at some point in time, so you might as well find it if you're trying to figure out, it's like those things that I tell you before. Write down the equations, draw your picture, do those things, and you start thinking about it. And if I'm in chemistry class, I say calculate the molecular weight because you're likely going to need it, and it allows your brain to think. Well, in this case, in statics, calculate the unit vector because you're likely going to need it. So it's one of those things that as you start working problems, when you don't know where else to start, find the unit vector because you're likely going to need it. So that gives us the piece. Okay, so that gives us our lovely unit vector. And remember that cosine squared alpha plus cosine squared beta plus cosine squared gamma all equals 1.
That's what I was thinking.
Yeah, that's a trig identity when we get to the third dimension. Okay? It's a trig identity when we get to the third dimension. And then we talked about now that's doing it that way. And then if we go ahead and do the other dimension, or we do it this way. Okay, so I've got a vector that looks like that. So let's look at that. Let's actually do a problem. And I'm making this problem up as I go, so we all know what happens when I do that, right?
It goes perfect.
Yeah, right. Never does. Okay. So I'm going to draw my coordinate system. So there's my coordinate system. Typically when we do this, we're going to use Z here, X here, and Y there. Now, that's not always the case, as you guys well know. It's not always the case. So I'm going to give myself a vector. Okay, so there's my vector. Now, your book can give you all kinds of fun ways to give you this vector. So, for grins and giggles, I'm going to give you that this is 20 degrees, and then I'm going to do my projection on this axis. And I'm going to tell you that that is 40 degrees. And I'm going to tell you the magnitude of this, and we're going to give it a force, and we're going to say this is a force. This is a force of 450 newtons. So there's my right angle there. I'm giving you that that projection is 40 degrees from the x-axis, which means this one becomes 50 degrees. But I don't necessarily need that, because I'm going to end up getting my triangle there. So if I want to write this vector in Cartesian form, okay, I want to write this vector in Cartesian form, F is going to equal, okay, F is going to equal, I need to know this side, okay, I need to know that side, which is also that side right there. So that's the adjacent side. So this is going to be 400, or if I'm in the K direction, this is 450 cosine 20 degrees. Now, I need to know this lovely, right? I need to know that lovely. That's this length right there. So this is going to have a, for I and J, they're both going to have a sine of 20 degrees playing into it. And then I'm gonna have my 450 for my x is gonna be cosine of 40. And my y is gonna be 450 sine of 40. Or, if you look at equation, this would be equation, this one doesn't actually have the numbers on it, that's interesting. In general, A is gonna equal A sine of phi, cosine of theta, in the I direction, A sine of phi, sine of theta, in the J direction, and A cosine of phi in the K direction, when this is our theta and this is our phi. So I could end up writing out that vector in those long pieces.
Is,
So that's this right here. So,
is phi and theta switched up? Are our numbers mixed up on the bottom? Our angles?
nope, because this is my phi. So there's cosine of 20.
Oh, okay, alright, I see.
So far, the only two new things that we've talked about is the unit vector, and now we're playing in 3 dimensions instead of just 2 dimensions, which is what we had been doing before.
This seems like it's more than
Do what?
This seems like it will not be a headache.
Well, you get used to it. Because we don't live in 2 dimensions, we live in 3 dimensions. Okay, everybody got that? All right. Trying to keep my notes nice and neat and everything. Just to keep you guys honest, okay, just to keep you guys honest, the quiz has 8 problems. Yeah, it's 8 problems. They should be fairly easy. It's over vectors. Pretty much that's over vectors in the first chapter.
Just 2D?
No. There's at least one 3D problem on there. At least one 3D problem on there. So let's look at this picture here. I'll give you this picture. So we got a picture, okay? We've got 2 vectors. All right, you've got 2 vectors, and the whole idea behind looking at this is being able to write these vectors out given from the picture. So all I'm really going to do on this one is not try to do a resultant, not try to do anything like that. I just want to be able to help you guys look at how the pictures are so we can translate the picture to a dimension. So let's look at this first one, right? So we got F1 is 500 pounds. So it's a force vector 500 pounds. The picture is telling us that we're pretty much in the XZ plane by itself. There's nothing in here to indicate that I am not in the XZ plane. So if I'm looking at this, my force 1 is going to have 0 in the I direction or 0 in the X direction. There's nothing there that's giving me my XZ plane. We are positive all the way around, so everything's going to be positive, so that makes life nicer to work with. So all of those are positive. So I've got positive in the J direction, and I have positive in the K direction. So now I've got that it's 500, and they didn't give us an angle, so I'm going to end up using my fraction. So if I'm in this direction, I'm in the Y direction, this is going to be 4/5. And if I'm in the K direction, it's going to be 3/5. So now I can clean that up. That's going to be 400.
Shouldn't it be opposite over hypotenuse?
This is my angle I want along the
Yeah.
Y.
Yeah.
That's adjacent over the hypotenuse. If I'm on the
Oh,
Y,
okay, cosine. Oh,
yeah, I'm on the cosine,
okay.
this is going to be 300. And I didn't even have to get my calculator out. If I'm working with the fractions, I didn't even have to get my calculator out. That's F1. All right, they gave us different information for the other one, right? They gave us different information for the other one. So first thing I got to worry about is how is it communicating? Well, first of all, I got to make sure I've got things correct in terms of my sign. So it's positive in the I direction. It's positive in the J direction. And it's negative in my K direction. Well, we just did one that kind of looked like that. So this is an 800 pounds, so this is going to be 800. And I want this length of my triangle. So that's going to be the sine of 45 degrees. Now, lucky for us, when sine and cosine of 45 degrees, right? So if I do cosine of 45 degrees, and I do sine of 45 degrees, should be 0.707, but we'll do it. This is equal to 0.7071, and this is 0.7071. Lucky for us, if we screw up here because it's a 45-degree triangle, we're going to be okay. But that's one of those places that if you're doing something in Chegg, and you're going through and you're going, okay, well, I got this one, but now they made this a 32-degree angle, and all of a sudden you're not getting it. It's because they don't tell you where the sine and the cosine are. And it works out this time that the sine and the cosine are going to be okay. So if I do that, I'm going to multiply that times 800. This is going to be 566K.
And we just use sine just because how the angle is given to us.
We use sine because that's how the angle is given to us.
Normally it's cosine, but they give us.
No, this is because I want this length.
Yeah.
I want this side. Now, we know that that happens probably going to be a 45-degree angle, so that works out okay. But this one, we're given this side, so it's the opposite. We got to use the sine. Now, that means the projection, okay? So I want to do F2 projected on the XY. That's going to be 800 cosine 45, which we know is going to be 566. That's the magnitude of this right here. That's 556. So if I do my X, that's going to be, my X is 566 cosine of 30 degrees. My XY is 566 sine 30 degrees. Because this is my projection onto the XY. Here's my X, and here's my Y. Now, I could have done it straight through just with the phi and the sine, but I wanted to get you guys used to dealing with a projection onto one of the planes, because that may help you down the road. So if I do that, 566 times cosine, that works out to be about 490. And then 566 times sine of that works out to be 283. So F2 in this case is going to be 490I plus 283J minus 566K. Now if we want to do the resultant, okay, so we want to do the resultant, I'm going to have FR is going to be 490I plus 683J minus 266K. Now I can find the overall magnitude. And I get that it's 881, and this will be in pounds, because our forces were in pounds. Now the question then becomes the angle. You have a question?
Yeah, and the resultant,
Mm-hmm.
how did you go from 183 to 683?
You're actually,
This one, 283, right? 283 plus 400?
Oh,
It's okay.
you was off screen, that's why.
Yeah, it's 400.
sorry. All right.
And then that's 566 plus 300 is a negative 266. That gives me 880, but now the question is angle, okay? Now, I can do cosine, if I want to do the alpha, beta, gamma, right? Cosine of alpha is equal to 490 divided by 881. Which means alpha worked out to be 56.2. And then you would do the same thing for beta and gamma. Now, a lot of times you have to be careful in how they ask the question, okay? So our resultant vector is going to be, if I do this and I come up here, our resultant vector is going to be something like this in here, right? It may ask you what the angle is projected into the negative zy plane. So you have to go and find that angle. So you've got to be careful in what mastering is going to ask the question, or what I'll ask the question, is to how to define that angle. So when we're looking at those resultant vectors and looking at how those resultant vectors are going to be, it's going to make a big difference.
To find our beta and gamma, would we also use cosine?
Yeah, because cosine of beta is going to be the 683 divided by the 881. Cosine of gamma is going to be the 266 divided by the 881. We good? Okay, let's do another one. This time I have a pole. Okay, and my pole is going to be on the y-axis. I'm going to define my z-axis here, and I'm going to define my x-axis here. So this is my x and z. Off the top of this pole, I have a stabilizing wire. Okay, and this gives me a point, so this is going to be point A, and this is point D. I also have a stabilizing wire that comes off over here, and this is point C. So I'm having to draw in a few things. We're told that if I draw a line from here to here, that angle is 20 degrees. And we're told that the angle that it's making going up is 60 degrees. We're told that the tension in the cable is 120 pounds. And this is the tension in cable AC. We want to write the force AC as a Cartesian vector. Okay? We want to put it in the X, Y, and Z. We want to do it as a Cartesian vector. So what we've got here is we've got a theta and a phi. So I can do f of x is going to be f cosine 60 degrees, cosine 20 degrees. So this is going to be 120 cosine 60 cosine 20. And that gives you 56.4 pounds. F of y is going to be my 120 sine 60, because this is y, not z. Okay? That's y, not z. And that equals, magnitude-wise, it's 103.9. And then f of z is going to equal 120 cosine 60 sine 20. It's going to give me 20.5 pounds. Now, the questions are going to be interesting, okay? We know that the tension in the wire is 120 pounds. Okay? The question is the components of the force exerted by this wire on the pole. The components of the force exerted on the wire are exerted by this wire on the pole. That means that if I'm doing that, we're looking at it on the pole, that magnitude has to be a negative on that one, and it has to be a negative on this one. Because this is, if we look at tension in the wire here, okay, look at tension in the wire there, on the pole it's going to be opposite that way, so it's going in the negative y direction, on the pole it's going down, and my z is positive over here, it's going backwards to that direction. And this is where you guys are going to get messed up most of the time, is figuring out those positives and negatives. So you have to really look at what the question is talking about, how the picture is drawn, what the question is. Because we can figure out components all day long. It's figuring out the directions that's going to be a little bit more tricky. And then, of course, you can do your angles. So the cosine of x, so if you do it in a different formation, instead of alpha, beta, gamma, this might make more sense to you, so this is another fun way to do it. You can do that. And if I do that, I get the 56.4 divided by the 120, and that's gonna give me, X is 62 degrees. And when I do the cosine theta y, you wanna make that negative, so that's negative 103.9 over 120, and that gives me 150 degrees. And then cosine of theta z, it's gonna be negative 20.5 divided by 120 is gonna end up giving me 99.8 degrees. So we'll be looking at Cartesian coordinate systems. That gets us through section 2.6 in the book, I think. You've got an in-class quiz on Friday, and then we'll be back at it on Monday, provided I can get back on the plane. Because I should be able to get back. I'm supposed to get back at 1:40, but you never know with the weather in the wintertime. So watch for Blackboard just in case. Which means, so that's kind of a keeping us ahead. Kyle, I will give Corbin, because you're coming to class on Friday, right?
Yes, I'll be.
Okay, I will give Corbin 4 balsa pieces for you. Okay? Because I want to hand out for everybody else. You can pick them up in the physics lab. These are the balsa wood pieces to make your trusses with. Because we'll start the truss project next week-ish in order to get there. And I will have to, Ed, I'll have to get you yours next week, but they don't take that long to get there. I meant to bring them last week when I came in, and I just messed up on that. But I know, Kyle, this will be the easiest way to get it. You can pick yours up on Friday. But that way, you get 4 pieces of balsa wood. You're gonna make 2 trusses. One is a standard design, and one is a design of your own making. I think I have everything put out in the mechanics class for it. I would prefer you use good old Elmer's glue, which does mean you're gonna have to deal with some drying time. We've done super glue. It works fast, it dries fast, but since we've got time, Elmer's glue works as well too. So looking at your trusses, the trusses can be cut with a box knife. They can be cut with scissors. They're good old balsa wood. So they've got it. And the wood will be on the instructor's desk in the physics lab. So if you wouldn't mind picking up 4 for Kyle, I would greatly appreciate it.
Okay.
Yeah.
Pulley system is due on this coming up Monday or the next one?
Pulley system is due, I thought I had it due January 31st. Maybe I have it due February 3rd. I have a lot of stuff due on January 31st, and I have stuff due on, so double check on whatever it is in Blackboard.
The 31st is a Friday, the 3rd is Monday.
I know, but it doesn't matter when I've got Blackboard to turn it in, so. Yeah, just check it. So I know it's not due Monday. It wasn't intended to be due Monday if I did. I think I have it due the 31st. I thought that's when I had it. But we will be breaking trusses on the 3rd. That's the idea there. We'll be breaking trusses, and then I'll be breaking trusses over in Enid that following Friday. That's why I'm not too worried about getting Ed his exactly at the same time. I will start doing for the trusses, just because the way trusses are, I think it's going to be better if everybody does them individually this time. And then when we get to bridges, we'll do teams. Partially just because I've had to make adjustments for my new equipment, and I've had to do all kinds of fun things. Okay? All righty, guys.